Hello and welcome to the inspiring online seminar series of TÜBİTAK Research Institute for Fundamental Sciences, which we organize for national and international audiences. Today is a very special day as our nation marks 97th anniversary of Republic Day. And today we have a very special speaker, namely Professor Bilge Yildız, a well-known scientist from the nuclear science and engineering and the material science and engineering departments at Massachusetts Institute of Technology, MIT, where she leads the laboratory for electrochemical interfaces. She's going to give a great talk about energy-efficient hardware for brain-inspired computing, artificial synapses based on proton and oxygen motion. The talk is part of our interdisciplinary seminar series. At the end of the talk, we will have a session for questions, where the questions can be asked by sending a message through chat button of the Zoom platform. Professor Bilge Yildız received her PhD degree at MIT in 2003 and her Bachelor of Science degree from Hacettepe University in Turkey in 1999. After working at Argonne National Laboratory as a research staff, she returned to MIT as an assistant professor in 2007. Her leadership responsibilities at MIT includes the Low Carbon Energy Center on Materials in Energy and Extreme Environments, and one of the integrated research group of MIT's NSF-sponsored Material Research Science and Engineering Center. Professor Bilge Yildız' research focuses on laying the scientific groundwork for proof-of-principle material systems for the next generation of high-energy devices for energy conversion and information processing. Her work has made significant contributions to advancing the molecular level understanding of oxygen reduction and oxidation kinetics on solid surfaces, and of ion and electron transport under electromechanical conditions. Professor Bilge Yildız' teaching and research efforts have been recognized by many awards. The Argonne Pace Setter Award, ANS Outstanding Teaching Award, NSF Career Award, SOMIA Award for International Collaboration in Materials Research, and Electrochemical Society Charles Tobias Young Investigator Award, and the American Ceramic Society Ross Coffin Purdy Award. With this, I want to thank once again Professor Bilge Yildız for joining us for this seminar and look forward to her work. Bilge Hocam, you're welcome to begin your talk, please.
Thank you so much. Çok teşekkür ederim Profesör Alikram, beni bu seminer programına davet ettiğiniz için. Ve sizin de dediğiniz gibi özellikle bu seminerin 29 Ekim'e düşmesi beni çok sevindirdi. Çok daha mutluyum bu günde bu konuşmayı sizinle paylaşabildiğim için ve hepimizin, tüm Türkiye'nin Cumhuriyet Bayramı'nı en içten dileklerimle kutluyorum. Ve umarım nice yıllara daha birlikte kutlayabiliriz. Evet.
Çok sağ olun, çok teşekkürler.
Ve Profesör Alikram bana bu konuşmayı Türkçe verip veremeyeceğimi sordu yaklaşık bir hafta önce. Türkçe vermeyi çok isterim ama maalesef bu konuların hepsini sadece İngilizce öğrenip çalıştığım için konuşmayı Türkçe vermem şu anda çok zor. Onun için İngilizce vereceğim teknik kısmını konuşmanın. Sonunda umarım bu bir sorun değildir ve konuşmanın sonunda eğer sorularınızı bana Türkçe sormak istiyorsanız nasıl rahat ederseniz, hangi dilde sormak isterseniz sorabilirsiniz. Umarım sorularınız vardır. Türkçe ya da İngilizce ne şekilde rahat ederseniz o şekilde sorabilirsiniz bana. Yeah, so let me share the slides. Do you see the slides?
Yeah, it's nice.
Okay, good. So with that, I will move to the technical part of the talk. And in the seminar, I will share with you our work on materials to enable energy efficient hardware for brain-inspired computing. And in particular, I will discuss about our work using protons and oxygens to enable artificial synapses in context of brain-inspired computing. So why do we care about this? The use of deep neural networks to accelerate machine learning applications, such as in natural language processing, computer vision, voice recognition, has been very popular. So it has big promise to accelerate developments in those directions. But it turns out that using our current computing platforms to perform those operations becomes extremely energy expensive. So I'm also in the nuclear department, right? And I like to joke that you need a modular reactor to go with each machine learning algorithm to recognize dogs from low resolution images. So it's really, really very expensive in terms of the energy need compared to how we humans process information in our brain. So we're talking about 6 orders or more higher energy power consumption that is needed for these operations compared to how we process data, which is simply on the order of 20 watts for an awake human, right? And the bottleneck for this challenge is the current computing architecture, which we call the von Neumann architecture, which separates the memory unit. So let me see if I can use a laser pointer. Yeah, which separates the memory unit from the processing unit. And there is a lot of data transfer between these two units back and forth. And this becomes the bottleneck that causes the very high energy demand for the matrix operations that go into implementing these machine learning algorithms. So the field is working on alternative computing hardware platforms in order to reduce the energy consumption in these operations substantially. And one such platform are physical neural networks that mimic the connectivity of the biological neurons. So simply by constructing arrays of crossbars where the bars are pretty much metallic wires, we can mimic the interconnectivity of the neurons, and the cross points of these bars are where we aim to emulate the synaptic behavior of the biological systems. And this cross point is very critical, and this is where we want to combine processing and memory, so that at the same location, so that you can evade this data transfer back and forth that is causing the super high energy consumption in the current computing architecture. So physical neural networks that have crossbar arrays that mimic the interconnectivity of the neurons, and their cross points that can emulate the synaptic electrical response is one way to address this energy challenge. And a critical component in this array are these cross points. And by imparting certain properties to these cross points, we can have computing, processing, and memory in the same location. And one type of device that could fit at these cross points is what we call resistive switches, with which we want to emulate the neuronal connections, the synapses, right? So what are resistive switches? Resistive switches are, let's say, devices which can function both as memory and a processor. But just if we take the memory function of it, this type of device can change its resistance state depending on its electrical history. So you have the same material, the same layer, but depending on the electrical history that you apply to that layer, the resistance can vary over a certain range. And there are different types of signatures we can obtain from such resistive switches. I showed two of these on this slide, on the left and on the right. So let's look at the left sketch, where let's trace the red curve first, which is a current voltage behavior. So we're applying voltage on the negative polarization, and we're tracing this red current curve, which is following a certain resistance value. And after a certain voltage, the current can substantially increase. And then I start following this green trace, where the conductivity is substantially greater than the red trace, right? So it's only this set voltage, a certain threshold voltage, that was needed to change the conductance of this element. Then I can reverse the voltage, trace the green curve, and at a certain positive voltage, the resistance can go back down to where I started from. So you have two different resistance states of the same material, depending on its voltage history. And this is one way that it can work as a memory, that it has an on state that could be 1 and an off state that could be 0, binary, okay? But these resistive switches don't have to work only binary. You can actually run them in a mode that can span a continuum of resistance states between the maximum and the minimum resistances. And that's what I show on the right. Now we are sending voltage pulses to a resistive switch. And with, let's say, on the pink region, with about 1,500 pulses of minus 2.5 volt, I can change the conductance from down here from a few to 1,000, which is 3 orders of magnitude increase in the conductance. And that is obtained via many, many states in between. So not just 0 and 1, but a continuum of states that we can obtain in between that allow us to process data then in an analog fashion, just like our synapses. And you can reverse the polarization and bring this conductance back down. And I will come back to the importance of this, of the ability to increase the conductance and decrease the conductance in context of biological synapses soon. Okay, so resistive switch whose electronic conductivity we can modulate by voltage history, either as 0 or 1, or a continuum of states that allow us to do the analog computing, where each of these states can become node weights in a physical neural network. So how do the resistive switches work? There are primarily 3 traditionally studied classes of resistive switching. And I show them here first before introducing the 4th one. So the first is the formation of metal dendrites, metal bridges, in an insulating solid electrolyte. And these metal bridges are drawn from a metal top electrode electrochemically. Okay, so you are applying a voltage, and electrochemically you can change the oxidation state and the position of the metal atoms via electromigration to form metal bridges that can then become the conducting path and change the resistance state. Okay, so metal conductive filament formation. A similar process that is conductive filament formation, but instead of metal, we are now working with oxygen vacancies. So the medium is an insulating metal oxide, and again, electrically, or rather electrochemically, you can create oxygen vacancies in this insulating oxide, and they form again a filament or a dendrite that is rich in electronic conduction around them and forms the electronically conducting filament. So metal filament or oxygen vacancy filament. A third process relies on electrically induced Joule heating and causing phase change between insulating and conducting states, conducting phases of a given composition. So we call these phase change materials, again, electrically induced, but the underlying mechanism is heating to change from one phase to the other. So these are quite popular processes that have been investigated so far. And in terms of the energy consumption, all three are a lot better than the current computing platform, but they are still not so low as we want them to be. And moreover, they have, especially the top two, the filamentary mechanisms, have challenges related to repeatability and therefore the reliability of these devices. Okay? So a fourth process that has become more interesting recently, that has come to our attention more recently, is via the intercalation of ions into a switching material. So this orange layer would be an insulating material, and we have a cation reservoir, such as lithium in your lithium-ion batteries. And just like in your battery, you can move those lithiums into this insulating layer and change the conductivity of this layer. And I will share with you in the rest of the talk our work on such cation intercalation-based inorganic synapses, as well as those based on oxygen vacancy conducting filaments. Either way, so whatever device we adopt and study, what are we trying to do? So I'm nowhere close to being a neuroscientist, but we're at least trying to understand what type of electrical signatures do we have in our neurons and in our synapses in the brain, so that we know what we are trying to emulate, right? So the key that we're after here is that the electrical transmission of signal from a neuron to a neighboring neuron relies on the electrochemical transmission of ions. And as you stimulate these neurons with electrical stimuli repeatedly, that gives rise to changes in the ease of signal transmission through the synapse. So the more you stimulate, the more you can strengthen the synapse, and that makes it easier to transmit signal in the following stimuli. And that permanent or either short-term or long-term change in the strength or change in the ease of signal transmission in these synapses is critical to the plasticity of the synapse. And that's an important element of how we memorize and how we learn things. And so I'm showing one example here taken from a biological synapse that is showing long-term change, permanent change in the ease of signal transmission through synapse. And that is quantified pretty much as an increase in the conductance of the synapse. Okay, so what they are measuring here is conductance before and conductance after sending a series of voltage pulses through the neurons to the synapse. And then they measure the conductance as a result of these pulses that are sent for a long time or shorter times or not. So the relative change from the left to the right that you see is showing us a permanent change in the conductance of the synapse. So that's the strengthening of the synapse. That makes then the following signal transmissions easier. And the longer time that they send these stimuli, the larger that relative strengthening is. So that is the green curve. The shorter that they send the stimuli, the weaker or even decaying behavior, so the loss of that strengthening, that's evident. So that's why we need to do many homeworks to learn a concept. You have to repeat to make it permanent and not to forget the next thing, right? So that's the analogy. And this type of increase in conductance with voltage stimuli is what we call potentiation. Potentiation, that is strengthening of the synapse. And transfer and accumulation of ions, in particular calcium, is a key process apparently in this increase of the synapse strength or increase of the conductance, in ease of signal transmission. So back about 10 years ago, researchers could emulate that behavior in an inorganic synapse. And I'm showing that here. So we are sending voltage pulses to a resistive switch. And after each voltage pulse, the conductance is increasing, and after a certain point, the conductance increase becomes permanent, just like in the biological synapse. But now it's an inorganic synapse that's actually working with this metal filament formation mechanism that I have shown to you. So that's a demonstration of this biological synapse potentiation, but in an inorganic device. And again, this is done by metal filament formation device, but as I've told you, there are challenges related to both still the energy and the reliability of these devices. And recognizing that these processes are enabled by neurotransmitter ions in our brains, including calcium, potassium, sodium, magnesium that are involved in this potentiation process. It makes us think that in solid state too, if we use these cations, we may be able to replicate the biological synaptic electrical signature. And in solid state, we have flexibility to electrochemically transfer, intercalate numerous ions as well, not only the biological neurotransmitters, but also others such as lithium and proton. Okay? And I will show to you that we will start with proton in this direction. Yeah, so we will go into looking at these ion intercalating resistive switches and whether we can obtain synaptic potentiation behavior with such devices. And we are not the first ones to have looked at this. In fact, there are a few recent works that have studied ion intercalation to modulate electronic conductivity, such as the potentiation of the synapse. But let's look at what they have done. So the first one on the left here is intercalating protons into an insulating material, but the protons are taken from hydrolysis of water, which requires very high voltages. And again, it beats the purpose of going to low energy. And moreover, it's not so practical to work with water in solid state computing platforms. The middle example uses an all solid state platform and lithium as the cation to intercalate. And this is pretty much a solid state battery, solid state lithium battery, where they are moving lithium electrochemically from the anode into the cathode of a battery. And the lithium level in the cathode, that is the lithium cobalt oxide, changes the conductivity of this material, and therefore they can see this potentiation and depotentiation behavior. Very nice work. And nevertheless, we hear from our industrial partners that lithium being very volatile species, it is more of a contaminant in their silicon fabrication foundries, and therefore lithium is not desirable to work with in the current computing chip fabrication platforms. So going back to proton, here is another very nice example where they have used proton, but with organic electrodes. So this P.PSS is an organic electrode whose electronic conductivity depends on the amount of hydrogens that you can input onto it. And so by shifting the electron, by shifting the proton from one electrode to the other, they could modulate again the electronic conductivity of these organic electrodes and show the synaptic potentiation and depression. The relative change in conductivities obtained is relatively small, and the conductances are very large to start with, which can make these systems leaky. But moreover, organic devices are again not quite conducive to integration with our current computing platforms. So organic is not quite easy to work with either. So that took us to our project where I was motivated by the proton being the smallest and the fastest cation, but with the need to be able to run this in an all solid state device without having to rely on organic materials or without having to rely on water. And so this is going to be the part where I will share with you our proton synapse work, which is in collaboration also with my colleagues, Jesus de la Lamo and Julie at MIT, together with our students and postdocs working on this program. So why proton? So this is the smallest cation that we can work with in solid state. It has nearly zero, if not negative, ionic radius compared to 0.9 angstrom radius of lithium. So you are dealing with the smallest ion that you can work with, and that gives you the advantage of lower energy needed to move the proton in solid state. And that should then translate to lower energy consumption in the device and also faster operating speed with the lower energy. That's why we wanted proton. But what do you do to incorporate proton in a reservoir and not have to deal with water? So for that, we have adopted a solid source. And if you look at this device sketch, again, it's pretty much a battery. It's a proton battery where we have a hydrogen source on the top, and in the bottom, we have an insulating material into which we want to intercalate hydrogens. And these two are separated by an electrolyte. And electrochemically, we can pull the hydrogen into the form of proton, and through the inner path, we can intercalate it into the insulating layer, and the electrons follow the outer circuit. And this reservoir for hydrogen can be a solid material, such as a metal hydride, and we have taken it to be palladium hydride to start with. Okay, so palladium hydride as our hydrogen source, and the resistive switching oxide we have taken to be tungsten oxide, which we know we can insert protons, at least from liquid electrochemical studies. And the separation layer, the solid electrolyte, as the fastest proton conducting electrolyte, that is naphthalene. And the device cross-section is shown here, which we have fabricated by thin film deposition of the tungsten oxide, of the palladium, and spin coating of the naphthalene in between. And how is this working? So let's look at the schematic mechanism first for the device. So we have the reservoir on the top, that is our proton reservoir, palladium hydride. If we apply positive potential in the reservoir, that is our gate, we oxidize hydrogens to become protons, which can conduct through the electrolyte and enter into the channel material. And the protons follow the inner path and the electrons follow the external circuit. And the entry of protons and electrons into tungsten oxide gives or donates electrons to tungsten oxide and increases the electronic conductivity, which I will also talk to you about. And we can reverse the process by applying negative potential at the gate, at the reservoir, and positive in the channel material. And this then pulls the protons and electrons back out of the channel material into the gate. And that depletes the hydrogen in the tungsten oxide, takes the electrons back, and leaves a more insulating tungsten oxide. That's the theory. And let's see if it works. So this is a few pulses that I'm showing to you now, gate pulses of +1 micron. And after each pulse, we are monitoring the conductivity of the tungsten oxide layer. And after each pulse, we are also opening the circuit. It's a non-volatile process because once you open the circuit, you block the path for electrons to escape. So after each pulse, we see progressive increase in the conductivity of the channel material. So upon each pulse that brings protons into tungsten oxide, we protonate the tungsten oxide and increase its electronic conductivity. So that's a few pulses, and let's look at this curve, which after 200 pulses inserts about 0.06 hydrogens per unit formula of tungsten oxide. And even this 6% hydrogenation gives me more than 2 orders of magnitude increase in the conductivity that I can obtain. And beyond this dilute regime of protonation, we can go to full protonation, that is from nil, so as prepared tungsten oxide, to full protonation, that is 1 hydrogen per unit formula of tungsten oxide, gives me this conductivity change that is more than 7 orders of magnitude. So this gives really us a large dynamic range of resistances or conductivities that we can modulate electrically, that is deterministic, and that goes exactly with the amount of hydrogen that we are inserting into the tungsten oxide. And in such a large range, if you want to work within such a large range, you can work with thousands of states depending on your electronic device sensitivity, measurement sensitivity. But really, it gives us a very large range of analog computing ability. And is it reproducible, reversible? That's also very important. And we can see that indeed we can obtain this potentiation and depression in a quite symmetric fashion, which is important again for use of this in reliable training of physical neural networks. And let's look at both of these curves. They are just in different ranges of protonation. That as we send protons with positive potential into tungsten oxide, we increase its conductivity. And this is exactly what I have shown to you in the biological synapse as the potentiation behavior. You're causing permanent changes in the conductance or in the strength of the synapse. And by reversing my environment, by reversing my polarization, we can pull out the hydrogen and depress the synapse, weaken the synapse. Okay, so we can capture both the potentiation as we insert hydrogen and depression or depotentiation as we extract hydrogen out of the channel material. And it gives us very good reversibility of conductivity, symmetric potentiation and depression, which is desirable for using them as inorganic synapses. And there are certain characteristics of these potentiation depression curves that are desirable for implementation in hardware, and they relate to the not only the range of resistance change, but how resistive we can make them to start with so that you're not dealing with leakages, and what are the differences in the minimum and maximum conductivities that determines how many states we can fit in between. And we have tested this in the different protonation regimes. So in the low conductance regime, which is low protonation, in mid conductance regime, which is, let's say, medium protonation, and high conductance regime, which is higher protonation. And you can see these 3 batches of curves that tells us that both the maximum to minimum conductance modulations that you can obtain with the same amount of pulses, and the shape of the curve, that is the symmetry of the curve, depends on where you are functioning the device, in which regime you are functioning the device. So without going into too much details, the point being we want high resistance, absolute high resistance, and symmetric potentiation, depotentiation that favors us to run the devices in this low protonation regime more favorably. Okay, so that's this panel. More symmetric curves and a relatively higher maximum to minimum conductances that we can obtain. How about the energy consumption, right? So I've motivated you to pay attention to this topic at the beginning of the seminar by saying that energy consumption matters a lot, and biological synapses are 6 orders of magnitude more efficient compared to our current computing platform. How about this device? What are we getting with it? And even though it's really our first demonstration and it's not really optimized, it's relatively thick layers that we are working with, And despite that, we have obtained a very low energy consumption per processed state that we could obtain with this system. So here I'm showing the resulting gate voltages that result from the gate pulses of currents that we send. And using this voltage current data, we could compute the energy consumption per unit area per state. And that comes to about 3.5 femtojoules per micrometer square device per state change. Okay? And if you convert that to per unit change in conductivity, it becomes nearly 20 attojoule per square micrometer per nanosiemens. So now if we compare that to the energy consumption per synaptic event in the device, in our biological synapses, that's on the order of few to 100 femtojoules. And even though we are dealing with this rather non-optimized device, if you are working with a micrometer device, the energy consumption becomes comparable to the biological synapse energy consumption. So this has motivated us really a lot to see, and that there is really a promising path here to run such inorganic devices, but with very, very low energy consumption when we are emulating the electrical properties of synapses. So a few femtojoule comparable to the biological synapses in the human brain. So those are the characteristics that we have obtained from the device. And we like to understand why things work the way they do in my group. And so we have also performed a number of experiments and theoretical calculations to resolve how we are inducing this resistive modulation in tungsten oxide based on its electronic structure as well as based on its atomic structure. And we can broadly hypothesize that when we are inserting hydrogen into tungsten oxide, hydrogen comes with a proton and an electron, and the electron fills into the 5D T2G band of tungsten that shifts the Fermi level up and increases carrier concentration and introduces higher conductivity, as long as we don't cause phase change, right? At least within the same crystal structure. So let's see if that's what we find. And in order to test that, we have performed X-ray photoelectron spectroscopy, both in the valence band and in the tungsten 4F region. And in the valence band, what we can see here is after protonation, formation of this additional state, which corresponds to the filling of the tungsten 5D T2G state, as I have introduced qualitatively in the previous slide. So formation of this in-gap state that increases electron donation and carrier concentration is one reason for the increased conductivity upon protonation. And that's also consistent, that electron transfer to tungsten is consistent with our finding of tungsten 5+ that forms after protonation, whereas before it's only tungsten 6+. So that's on the carrier concentration increase. We have evidence to also mobility increase, and one of that is through looking at the oxygen K-edge X-ray absorption spectra. And without going into details, what we see here is that some of these features, especially the first feature, is a measure of tungsten oxygen hybridization. And after protonation, we see an increased hybridization, and the states of that hybridization being in the conduction band means that you also have increased electron mobility. And furthermore, at high hydrogen concentrations, we see a transition from monoclinic to tetragonal structure, which comes with increased crystal symmetry, which can also contribute to increased mobility. So complementary to those is the change in electronic structure that we could probe theoretically. To start with, tungsten oxide is a semiconductor with 2.2 eV band gap. With a small amount of hydrogen insertion, we see the formation of in-gap states, shallow in-gap states that can serve as N-type donors, and they take place the form of large polarons. And if we increase the hydrogen content above 10%, this delocalizes the electrons and the material becomes metallic, and the structure also becomes more symmetric, consistent with the experiments I have shown to you on the previous slide. So the N-type doping and the symmetry increase that transitions to metallic is what we see from our simulations, which is consistent with the spectroscopy and diffraction measurements. So in summary, on this protonic electrochemical synapse, I've shown to you that we could come up with rather a proton battery, which deterministically injects protons into and out of an insulating layer that modulates its electronic conductivity, that gives us the ability to potentiate, increase the conductance, increase the synapse strength, and depress, weaken it. And we can do this with a very low energy consumption, as I have shown to you, comparable to biological synapses, thanks to the fast mobility and low barriers needed to move proton. And not only that, we could demonstrate it as a device that could emulate synaptic potentiation, but we could also explain the mechanisms based on charge carrier density increase as well as mobility increase. And we're continuing to work on this device to optimize its device design configuration, but also explore alternative materials, especially replacing naphion with completely inorganic proton conducting electrolytes, and also encapsulating this device to block hydrogen escape. So with that, let me move on to, and I know I have less time left now, to the oxygen vacancy conducting filament type resistive switches, and what the problem there is and what we are trying to do. Okay. So the challenges with these devices that change their resistance by oxygen vacancy filament formation is the large variability or lack of repeatability. And by that, what I mean is large changes in the conductance states that you obtain with the same voltage, or changes in the set reset voltages that vary from device to device, such as seen here for readout resistance that varies more than an order of magnitude for the same material, but different fabricate or different elements. It should in theory be the same, but they're not the same intrinsically. And variability of these properties, even in the same device. So when you cycle to switch it on, off, you get a range of resistance values. That should not be. That should not be, because this type of variability limits the accuracy of the physical neural networks that you are trying to train based on these switches. So if you have, for example, a 10-fold variability, you have 100% error in the training. If you have just 3-fold variability, you are limited to just 90% in accuracy. So you really need to understand where this variability challenge is coming from and see if we can control it, right? So the biggest question here is, I told you they form these vacancy filaments that are conducting, but where on earth are those filaments forming, right? So that is the biggest question, and that arises from the microstructural and chemical variabilities that are inherent in the materials that we make into these resistive switches. So these are typically oxides that are deposited via different routes, that form non-uniform microstructures, that form non-uniform distribution of defects in them, that then gives rise to stochastic formation of these filaments. So you don't know where the filament is, and therefore you cannot control it. So what can we do? We are thinking of different ways to localize the formation of these filaments, either by engineering the microstructure or by engineering the chemistry. And I will share with you our work on the latter briefly. And that will be based on implanting dopants that can localize the formation of these conducting filaments more strongly. And this work is in collaboration with my colleague, Nicholas Fang at MIT, and our students who have worked on this topic. And the peculiar observation that Professor Fang and his student had before they came to us to explore what's happening is the following, that they're using an aluminum oxide as a resistive switching layer. And if they do two things, the switching becomes much more consistent. That is, dividing this relatively thick layer into even thinner layers, but that's not enough. On top of that, ion mill through the gold that is deposited as the contact on top of it. So focused ion beam milling to define the device area makes a big difference in the repeatability. So let's see what we mean. So if you look at this current voltage curves, if you do not mill through gold, you get very large variability on the set reset, on the amount of resistances. It's all over the place, like it's not a usable device. But if you mill through the gold layer, the cycling becomes very repeatable. And this is the ideal signature that you want to obtain. Okay, so something happens when you mill through the gold. And our hypothesis is that milling through the gold implants gold atoms into the alumina. And gold being a high electronegativity element makes it easier to create oxygen vacancies near it. And this may be one way to localize preferential paths for formation of conducting filaments. And with the same argument, we can then hypothesize high electron affinity metals such as gold, platinum, and palladium can improve the repeatability by localizing oxygen vacancies, whereas copper, titanium, and aluminum, regular transition metals, should not do it. Okay. So our work here has been primarily computational, which were then verified, validated by our experimental collaborators. And what we are seeing here first is that one can significantly reduce the formation energy of oxygen vacancies if you implant metals like gold, platinum, and palladium into alumina, which is very difficult to form oxygen vacancies alone, right? Because it tries to form F centers, and this is difficult for alumina, and the energy to do that is very expensive. But if you insert gold, platinum, palladium, which can uptake the electron, the ease of vacancy formation becomes really good compared to other transition metals, which are not nearly as good in reducing the vacancy formation energy compared to high electronegativity elements like gold, platinum, and palladium. So that's point one. We can reduce the formation energy of oxygen vacancies. So what else do we see here? What is gold really doing? So when we insert gold into alumina by looking at this electronic density of states, we can see that gold is introducing these in-gap states that when you form oxygen vacancy, they can pick up the electron left behind, and these states can pick up the electron left behind and lower the state energies. And we can see that from the charge analysis that gold, once you create an oxygen vacancy, picks up electron, or even without the oxygen vacancy. So gold picks up electrons, it becomes negative, and this electron comes both from the aluminum and oxygen, which become less in charge compared to the undoped case. Okay, so on one hand, that lowers the aluminum oxygen bond strength and makes it easier to remove the oxygen. But even more importantly, it's gold that picks up the electrons after removing the oxygen. And we can see that in this partial charge density of gold states after forming the oxygen vacancy, which are really picking up that excess electron and not having to deal with forming an F center and that substantially reduces the energy to create oxygen vacancies. And not only individual vacancies, but we can also form vacancy clusters, which is important in forming networks or filaments of conducting paths made of vacancies. So vacancy cluster formation, as well as vacancy cluster binding around these metals, becomes more favorable when you're dealing with high electronegativity elements. And again, these clusters introduce a large number of in-gap states that can form the building blocks for conducting paths. So you have gold that favors to form and bind oxygen vacancy clusters, and they introduce in-gap states to provide the electronically conducting units for the network or for the filament. And we could validate these experiments, these computational predictions experimentally, where high electronegativity elements like palladium, gold, platinum, when implanted into alumina, shows much better repeatability of the switching cycles, whereas with copper, excess aluminum, or titanium, we cannot improve this cycling stability, repeatability, and that goes back to my argument that these high electronegativity metals makes it easier to form oxygen vacancies by picking up the electron left behind from oxygen. And that gives rise to strong binding sites that are localized and allows to use these building blocks to form conducting filaments or conducting networks. So having shared both of these paths of studies, what else can we think, right? So one last word on the outlook, right? So I've shared with you our work on ion intercalation devices and oxygen vacancy filament devices or materials. So I believe this former that gives rise to bulk uniform switching is very, very exciting because it solves this outstanding issue of unrepeatability and inability to control the filament that has been really a roadblock for the large-scale implementation of these filamentary devices. So I think for that, it's very promising, and I really urge us and the field to look more into this type of mechanism and device. And moreover, I've shown to you this with Proton, but you can intercalate numerous cations into insulating materials. And in fact, we are starting to work with also those cations that are the neurotransmitters that I have mentioned to you about in our biological synapses. So by using such cation intercalation that are relevant to our brain fluid as well, maybe in the long term, we can go from brain-inspired computing to brain-assisted hardware or computing, potentially to help with the treatment of neurological diseases by integrating these systems to brain tissue. Nevertheless, this is a very new direction. The ion intercalation system is very new, it's very promising, but it has many untested aspects as well. Therefore, in parallel, I'm still very excited about the ability to control and engineer point defects that could give us the potential to control the formation and repeatability of these filamentary devices. So broader field of point defect chemistry, point defect engineering should be adopted more deeply into these electrical devices. The two fields would benefit a lot from working together more closely. So I will end here, and I will again say that I'm very happy to give this talk on this very beautiful day, and thank you for listening.
Çok teşekkürler Sayın Hocam. Bu kadar güzel, değerli ve derin konuları kapsayan bu değerli konuşmanız için.
Teşekkür ederim.
Sorular arkadaşlar. Şimdi soruları hocamız Türkçe'de alabilirim dedi. Lütfen.
İngilizce'de sorabilirsiniz.
Evet, nasıl uygun görürsünüz öyle işte. Veya elinizi kaldırarak direkt de sorabilirsiniz soru. Lütfen buyurun.
Ben herkesi göremiyorum. Eğer
İşte siz de bakın hocam. Ben bakalım
hocam,
mesaj gelecek.
Siz de çağırabilirsiniz soru sormak isteyen.
Evet. Bir soru var işte. Görür müsünüz Sayın Hocam?
Görmüyorum ama o chatte. Tamam, bir saniye.
Yani chat'in üstüne tıklayan çıkıyor.
Berke asked, what are the differences between microstructure engineering and dopant engineering? So this is related to this last piece on the filamentary devices. So microstructure engineering is to control, for example, the crystallographic texture, grain orientation, grain size, grain boundary distribution. And I say that because extended defects such as grain boundaries or dislocations in such oxides are typically easier to reduce, easier to form oxygen vacancies in, right? And if you start with a very random microstructure, these filaments can form anywhere in any paths with different properties. But if you have a very uniform microstructure, so let's say a well-defined crystallographic orientation, well-defined and a narrow distribution of grain boundary types, then you can actually narrow down the distribution of switching properties. And on top of this, if you add dopant engineering, that is what I've shown in the last slides, where we are inserting dopants that are, regardless of the microstructure, are chemically so distinct that they can strongly localize the formation of the vacancy. So aluminum being in gold being in aluminum makes such a big difference in the ability to pick up the electron of an oxygen after you remove the oxygen, that reduces the vacancy formation energy, or that makes it much easier to form the vacancy, becomes a pinning site. So that's what we call dopant engineering, that we are inserting these additional elements that are chemically very distinct from the host and can really pin the formation of these vacancy conducting paths. I hope that helps to clarify.
More questions, please.
Yeah, feel free to ask anything. We are all learning. Okay, Berke is happy. She said she understood it. So excellent. Okay. Other questions? There is one more question. Okay. Nörolog olarak yeterince takip edemedim ama yapay sinaps ve bunu biyolojik alanlarla bağlantılı hale getirilebilmesi heyecan verici buluyorum. Teşekkür ederim. Evet, ben de bu konuda epey heyecanlı ve ilgimi çeken bir konu. Ve yani bizim kullandığımız device'ları değil ama daha traditional transistörleri beyinle communicate etmek için çalışmalar yapılıyor aslında bu alanda. Ama hepsinin tabii ki değişik özellikleri var, değişik advantage, disadvantage'leri var. Ama hiçbiri direkt brain fluid ve direkt neurotransmitterlerle çalışan device'lar değil. O yüzden ben bu ionlarla çalışan electrochemical device'larımızı çok ilginç buluyorum. Uzun vadede o alana katkıda bulunabilirler belki diye. Ama ben sizin gibi nörolog değilim. O yüzden ne dediğimi bilmiyor da olabilirim. Fakat bir olasılık var orada connection için. Ben de öğrenmeye çalışıyorum.
Çok iyi.
Evet, başka sorularınız varsa heyecanla bekliyorum.
Hocam merhaba, benim bir sorum olacaktı.
Merhaba.
Merhaba hocam. Öncelikle teşekkürler konuşma için. Herkesin bayramı kutlu olsun. Hocam
Tamam.
ben daha çok bu protonic electrochemical synapseslerle ilgili bir sorum olacaktı.
Evet.
Şimdi oradaki electrolyte malzeme nafyon.
Evet.
Sıcaklık çok düşük olduğunda bu tür transferler çok rahat. Ama yerine bir inorganik bir kristal koyduğumuzda zirkonya ya da işte Sirya bazlı şeyler, bu tür yapılarda protonun iletildiğini nasıl izlersiniz?
Çok güzel bir soru. Biz de tam bu sorduğunuz konu üzerine çalışıyoruz. Ve dediğiniz gibi Sirya veya baryum zirkonate yüksek sıcaklıkta proton conduct edebilen malzemeler, değil mi? Evet. Lattice içinde yüksek sıcaklıkta proton hopping üzerine. Ama bu malzemelerin grain boundary'leri düşük sıcaklıkta water absorb edebiliyor. So, hydroxylation layer gibi düşünebilirsiniz. Ve düşük sıcaklıktaki proton conductivity'leri bu absorbed water layer üzerinden oluyor. Biz bu özelliğini kullanarak bu malzemeleri böyle device'lara integrate etmeye çalışıyoruz. Ve sadece Sirya ve zirconate değil. Şimdi bu konuya baktıkça daha çok anlıyorum ki hangi oxide malzemeyi alsanız bu oxide üzerine water absorb edebiliyorsa low temperature proton conductivity oluyor.
Hocam da bu kristallerde biliyorsunuz ki 600 derecenin üzerine çıkmamız gerekiyor. O zaman
aynı mekanizma olmuyor işte. 600 derecesinde değil, room temperature'da absorbed water'ı kullanarak proton conductivity elde edebiliyor.
Tamam.
Bu şekilde sadece Sirya, zirconate falan değil, böyle deadly insulating malzemeler, alumina, silika, bunlar bile proton conducting oluyor. Onları nafyon yerine integrate edip bu device'ı ilerletmeye çalışıyoruz şimdi.
Tamam.
Çünkü sizin gözlemlediğiniz gibi nafyon oda sıcaklığında en hızlı proton conduct edebilen malzeme ama gene de polimerik bir malzeme.
Evet.
Bunu silicon foundry, chip manufacturing platformuna integrate etmek için back-end of the process yüksek sıcaklık gerektiriyor. Nafyonu bozabiliriz o arada. O yüzden gerçekten bu nafyonu inorganik bir proton conductor'la değiştirmemiz gerekiyor. Ve belki bir sonraki konuşmamda bunları da paylaşabilirim sonuçlarımızı. Ama dediğim gibi bu yüksek sıcaklıktaki proton conduction mekanizmle room temperature'daki proton conduction mekanizm birbirinden farklı. Room temperature'daki sadece absorbed water layer üzerine çalışan bir proses ve herhangi bir oxide işimize yarayabiliyor orada.
Tamam hocam, teşekkür ederim. İyi akşamlar.
Ben teşekkür ederim. Başka sorularımız?
Bir kişi de el kaldırmış.
Buyurun.
Cumhuriyet Bayramımız kutlu olsun.
Cumhuriyet Bayramımız kutlu olsun. Sağ olun. Berke, ilk soruyu soran sendin o zaman. Değil mi? Chat'te gönderen sen miydin?
Evet, sanırım ta kendisiydi.
Evet, tamam. Memnun oldum gördüğüme seni de.
Ben de sizi gördüğüme memnun oldum.
Çok güzel.
Teşekkürler. Başka sorular arkadaşlar var mı?
Ve şu anda... evet, buyurun.
Buyurun lütfen. Şu anda başka soru ben göremiyorum. Siz görür müsünüz hocam başka soru?
Ben de ona bakmaya çalıştım. Chat'e bakalım. No. Şu anda gelmiyorsa aklınıza soru, daha sonra bana bir şeyler sormak istiyorsanız ya da herhangi bir şekilde size yardım edebilirsem hiç çekinmeden benimle irtibata da geçebilirsiniz daha sonra. E-mailim grup web sitemizde, faculty web sitemde. Herhangi bir zaman sorularınız varsa bu konuyla ilgili ya da başka öğrenmek istediğiniz konularda hiç çekinmeden bana yazabilirsiniz.
Ben de bir şey eklemek istiyorum Sayın Hocam. İşte herkes duysun diye Bilge hocamız inşallah bu Covid belası dünyadan çekip gittikten sonra Temel Bilimler Araştırma Enstitüsü'nü ziyaret edecektir. O zaman daha yüz yüze ortamda bu tür çok derin konuları tartışma imkanımız olacaktır.
Tabii ki.
Umarım bu çok uzun zaman almayacaktır. Covid
Ben de umarım. İnşallah en kısa zamanda.
inşallah en kısa zamanda. Hocam sorular yoksa tekrar size içtenlikle teşekkür ediyoruz ve burada bitirebiliriz eğer sizin için de uygunsa.
Tabii ben de çok teşekkür ederim bana bu fırsatı verdiğiniz için. Ve tekrar hepimizin Cumhuriyet Bayramı'nı en içten dileklerimle kutluyorum. Hepiniz sağlıcakla kalın ve görüşmek üzere.
Çok teşekkürler hocam. Sizin de bayramınız kutlu olsun. Siz de kendinize dikkat edin, sağlıcakla kalın. İnşallah görüşeceğiz. Sağ olun.